Ever wondered what a speeding car, a football soaring through the air, and a planet orbiting the sun all have in common? Well, it turns out they all follow the exact same invisible rulebook. In this explainer, we're going to pull back the curtain on the fundamental principles of motion and see how they literally shape everything around us.
So here's our game plan. We're going to start by learning the actual language of movement. Then we'll dive into what causes it in the first place. After that, we'll get into the nitty-gritty of momentum and energy. And to wrap it all up, we'll see how these rules come together in the real world to save lives on the road every single day. Let's get into it.
Okay, first things first. To really understand motion, we need a way to talk about it, a language to describe it. That's where kinematics comes in. It's all about the what. How fast, how far, how an object's speed is changing, before we even touch on the why.
Now, before we measure a single thing, we have to agree on our point of view. Think about it. Are you measuring the speed of someone walking down the aisle of a moving train relative to the train itself, or relative to the ground whizzing by outside? That choice, that point of view, is your frame of reference. It's the first rule we have to learn: all motion is relative.
This table here, it's basically a secret decoder ring for motion. When you plot things like displacement or velocity against time, you can tell a whole story just by looking at the graph. For instance, if you're looking at a velocity time graph, the steepness of the line, the slope, instantly tells you the acceleration. And the area underneath that line, that's the total distance you've traveled. Each graph gives you a different, really powerful piece of the puzzle.
So, how do we figure this stuff out without having to draw a graph every single time? Well, say hello to your new best friends, the SUVAT equations. These four formulas are the workhorses of kinematics. The cool part is, if you know any three pieces of information about an object's motion, you can almost always use one of these to figure out a fourth. They're like our mathematical toolkit.
But, and this is a big one, there is one golden rule you can never, ever forget. These equations only work if the acceleration is constant. Think about a car applying its brakes smoothly, not jamming them on and off. If that acceleration is all over the place, this toolkit is useless. So, before you ever use them, you have to ask yourself, is the acceleration steady?
Okay, so we've got the language down for describing motion, but why does anything move in the first place? What makes an object speed up, slow down, or turn a corner? The answer to that question is the hero of our next section, force.
Turns out, forces pretty much come in two main flavors. You've got your contact forces, things that require physical touching, like the friction between your shoes and the floor. And then you have the mysterious, almost magical non-contact forces, like gravity, that can pull an apple from a tree without anything touching it at all.
And the person who wrote the definitive rulebook on forces was, of course, Sir Isaac Newton. His three laws are the foundation. Law 1 is inertia, which is really just the law of stubbornness. Things want to keep doing what they're already doing. Law 2 is the famous F equals ma. It says that if you want to make something change its motion, the more force you use, the more it accelerates. And Law 3, action-reaction, for every push, the universe pushes back just as hard.
All right, now let's take two ideas we already know: how heavy something is, its mass, and how fast it's going, its velocity, and combine them into one incredibly useful concept. We're talking about momentum, which you can just think of as a measure of an object's unstoppability.
The formula itself is super simple. Momentum, which we call P, is just mass times velocity. But this is why a massive, slow-moving truck can have just as much momentum as a tiny speeding bullet. Now, which one would you rather try to stop? Yeah, that truck's combination of mass and velocity gives it a whole lot of unstoppability.
So how do you change an object's momentum? Simple. You apply an impulse. And as you can see from this equation, an impulse is just the force you apply multiplied by the amount of time you apply it for. Think about hitting a baseball. It's not just how hard the bat hits the ball, it's also about how long the bat stays in contact with it. That relationship between force and time is the secret sauce to so much in physics.
And all of this leads to one of the most powerful, fundamental laws in the entire universe, the law of conservation of momentum. In any interaction, like a collision, where no outside forces are messing with things, the total amount of momentum you start with is exactly the same as the total amount you end with. It doesn't disappear, it just gets redistributed among the objects.
So we know forces cause changes in motion, and momentum helps us keep track of collisions. But what pays for all this to happen? What's the fuel? The answer is energy. You can really think of it as the universal currency that makes everything happen.
Now, in physics, the word work has a very, very specific meaning. It's not about how tired you get. You could push against a solid brick wall all day long, get exhausted, but if that wall doesn't move, you've done zero work. Work is only done when you apply a force that actually causes something to move. It's literally the act of transferring energy.
When we're talking about motion, we're mostly dealing with two key types of energy. Kinetic energy is the energy of doing something. It's the energy an object has because it's moving. Potential energy, on the other hand, is the energy of waiting. It's stored energy, like a book you're holding up in the air, just waiting for you to let go. A really cool type of potential energy is what you find stored in things like springs or rubber bands. And Hooke's law here gives us this beautiful, simple rule for it. The more you stretch or compress a spring, the stronger its force, trying to snap back to its original shape. It's just a wonderfully elegant relationship. And you guessed it, just like momentum, energy has its own unbreakable conservation law. And this one is probably the most famous law in all of science. Energy cannot be created or destroyed. It can only change its costume. Transforming from the potential energy of a roller coaster at the very top of a hill to the kinetic energy of its wild ride down. But the total amount of energy in that system always stays the same.
All right, now for the grand finale. This is the payoff. We've talked about motion, forces, momentum, and energy. So let's put it all together in a place where these rules aren't just academic. They are literally the difference between life and death. Let's talk about car safety.
So when you have to slam on the brakes in your car, the total distance it takes to come to a stop is actually made of two separate parts. First, there's the reaction distance. That's how far your car travels in that split second while your brain sees the danger and tells your foot to move. Then comes the braking distance, which is all about pure physics. This brings us to the most important question. We all know that things like airbags and the crumple zones on cars are there to protect us. But how do they actually do it? What's the physics behind how they work their magic? Well, the answer is just brilliant.
The whole secret is hiding in that impulse equation we saw a few minutes ago. Think about it. In a crash, your change in momentum is fixed. You're going from 60 miles an hour to 0. That's a done deal. So if the change in momentum, delta P, is constant, that means force and time have an inverse relationship. If you want to make the force smaller, and believe me, you really want to make the force smaller, you must increase the time of the impact.
And that's it. That's the whole trick. A good crash is a slow crash. Airbags and crumple zones are engineered with one single goal: to increase the amount of time it takes for you to come to a complete stop. By stretching that violent impact out over a few extra crucial milliseconds, they massively reduce the peak force that gets transferred to your body. Less force simply means less injury. It's physics, in action, saving your life.
So, the next time you're in a car or you watch someone throw a ball or even just walk down the street, take a second. The entire world is moving according to these elegant, powerful rules. The real question is, now that you know them, what invisible forces are you going to notice shaping your world?